Hello great aspirants, welcome to part 10 of Thermal and Statistical Physics series. Question number 5. Consider a one-dimensional gas of n non-interactive particles of mass m with the Hamiltonian for a single particle given by h is equal to p square by twice m plus half m omega square x square plus 2x. The high temperature specific heat in units of R is. Here we can complete this square. So this will be x square plus 2x plus 1, and then we can subtract this term minus 1. So h will be equal to p square by twice m plus half m omega square. So this will be x plus 1 square minus half m omega square. So this is simply a constant. So let us find out its average energy. So average energy will be average over p square by twice m plus we have this term. So this is a simple harmonic oscillator which has just this shifted origin over here. This will be half m omega square x square plus 1 square, and this part is constant. So this will be equal to half kBt. For this, for each quadratic term, we will have half kBt contribution. So plus half kBt. So this will be equal to kBt. So total energy will be n into kBt. For n particles, it will be n kBt. So specific heat capacity du by dt, this will be equal to n into kB. So this is 1 into n into kB. So option A is correct. Next question. A large number n of ideal bosons, each of mass m, are trapped in a three-dimensional potential V of R is equal to half into m omega square R square. The bosonic system is kept at temperature T, which is much lower than the Bose-Einstein condensation temperature Tc. The chemical potential mu satisfies. So for this, let us find out its energy. So this will be Nx, Ny, Nz. It is in three-dimensional potential, and this is harmonic potential. So this will be Nx plus half plus Ny plus half plus Nz plus half into H omega. So for ground state, because temperature is much lower, so we will consider ground state E00. So Nx is 0, Ny is 0, Nz is 0. So this will be simply 3 by 2 h cut omega. So as the temperature is much lower than this Tc, the chemical potential is very close to this ground state energy. So that means it will be equal to 3 by 2 h cut omega, and it will be even less than that. So mu will be less than or equal to 3 by 2 h cut omega. So option A is correct. Next question. In a thermally insulated container, 0.01 kg of ice, so 0.01 kg of ice at 273 Kelvin is mixed with 0.1, it is mixed with 0.1 kg of water at 300 Kelvin. Neglecting the specific heat of the container, the change in entropy of the system is, in attaining thermal equilibrium is. So here we have to find change in entropy. That means we have to find entropy change for ice as well as for water and add those two. So we have mass of ice. So ice is first melted and then its temperature will reach some final value. So for melting of it, it will be mass of ice into latent heat plus mass of ice into mc delta T. So into C into we have final temperature, let it be T, initial temperature is 273. This will be equal to mass of water into C into final temperature is 300 minus T. We have to solve this equation for T. So this will be 0.01 into latent heat is, this is 335 kilojoule. So this will be 335 into 10 raised to 3 plus 0.01 into its specific heat is 4.2 kilojoule. Or let us write all these things in kilojoule only. So this will be 335 plus 0.01 into 4.2 into T minus 273. Here we have 0.1 into 4.2 into 300 minus T. So this you have to solve for temperature. So from here you will get, after solving this equation, temperature is equal to 290.29 Kelvin. Now delta S is equal to delta S of ice plus delta S of water. For ice, it is melting as well as this temperature increase. So this will be m ice into L upon temperature of ice plus this will be m ice into C into ln of temperature, final temperature upon initial temperature, plus m omega C ln of final temperature is T, initial temperature is TW. So just substitute all these values. So we will get this first term, this thing, this comes out to be 14.85 and this is equal to minus 13.82. So this is equal to 1.03 joule per Kelvin. So answer is 1.03 and answer in the answer key is 1.02 to 1.04. Next question. Here we have used this formula, delta S is equal to mc ln of Tf upon Ti. And derivation for this I have done in previous video. Next question. Consider two systems A and B, each having two distinguishable particles. In both the systems, each particle can exist in states with energy 0, 1, 2 and 3 units with equal probability. The total energy of the combined system is 5 units. Assuming that the system A has energy 3 units and system B has energy 2 units, the entropy of the combined system is Kb ln lambda, where the value of lambda is. So here it is given that Ea is equal to 3 and we have 4 energy levels, that is 0, 1, 2 and 3, and we have 2 particles and they can be any of these energy levels, but the condition is total energy should be E. So if one particle is in 0 state, then second one has to be in 3rd state, or this will be AB, or they can be in 2, 1 states, so A, B. So there are such 4 possible combinations. So number of microstates in A is 4. For the second case, same 0, 1, 2 and 3. Now we have here EB is equal to 2. So this can be AB or BA, or it will be AB. So here number of microstates in B is equal to 3. So 3 cases are possible. So total number of microstates is product of microstates. So that is 4 into 3, which is 12. So entropy is equal to Kb ln of omega. So that is Kb ln of 12. So from here lambda is equal to 12. So answer is 12 and answer in the answer key is 12 to 12. So these were all the questions from GATE 2019 paper. If you like this video, please give it a thumbs up and subscribe to my channel for more videos. Keep learning.